Hi everybody, welcome to your first BC topic. It's Euler's method. Euler's method is the first numerical method that you're going to see in differential equations. So in college, if you take the course differential equations, you're going to learn a lot of numeric methods. Euler's method is probably the first you'll see, and Euler's method goes directly with differential equations. So it's one of the last topics you'll need in DiffyQs. I'm going to come back to these visuals. They won't make sense until you get a little background info. These are the notes you're going to need for Euler's method. I want you to write all these down, do it neatly. That way we don't have to do it in class, and then you have this to look back on later on. So the idea behind Euler's method is it's going to give us an approximation for the solution of a differential equation. The key is when we can't solve it by hand. So we've been solving separable differential equations by hand. There's lots of examples of separable differential equations, but this is an example here. You get the x's on one side, the y's on another. There are also examples of differential equations that cannot be separated, usually when x and y are added. In this case, you have no idea what y is. You can't find what y is. You could graph a slope field and visualize what y is, or you could use Euler's method to actually plot points approximating f through the slope field. So you're basically following the slope field and actually plotting points to approximate what the curve would look like. Okay, so you can pause now and write, or write now and pause later, however you want to do this. Either way, I'm just going to highlight the key points here. Euler's method only works because of the idea of local linearity and linearization. Local linearity, remember, says if you zoom in on any curve, it's going to look straight. If you zoom in a lot, and you're going to be connecting multiple small little line segments to make an approximation of the curve. You'll plot a bunch of points, they'll be close together. The closer the better. You're going to connect them to make line segments, and that will approximate your curve. So again, you're basically following the lines in the slope field. You already know what slope fields are. Now we're going to plot within the slope field. A couple things to note here when it comes to accuracy. The farther that you get from your initial condition, which is where you start, the less accurate that your approximation is going to be. Another thing is if your curve is concave up, the approximation will be below the x-axis, and if your curve is concave down, the approximation will be above the x-axis. We've already talked about stuff like this before when we did linearizations. If we have a concave up curve and we have a tangent line, that's below. If we have a concave down curve and we have a tangent line, then your actual function values are below and the approximation is above. The approximation is on the tangent line, remember. So on the AP exam, you're going to be practicing several AP problems here. You're only going to be able to do Euler's method if they give you a differential equation, dy dx. They have to give you some ordered pair, an initial condition. They might write it as f of something. F of something equals something. They might write it as y of something equals something. And they're going to give you a step size. They usually refer to it as step size. We're going to be calling it h here. That's common, and if you do it in the future, they're probably going to call it h in your future DiffyQ book if you take the class. So again, h is what we're going to call that distance along the x-axis, and it's the distance between the points. So h would be, where's my pen? H would be this horizontal distance and this horizontal distance. Was there anything else? I can't find my pen. Here it is. All right. All right. So the most important thing you're going to want to write down is this here, because this is the key to what you're going to be doing. So pause the video, write this down, and then come back and I'll highlight a few key things. So slope fields, you can think of it as like a signpost. If you're walking along the road and you stop, you see a sign, it points and tells you where to go. When you do Euler's method, you have a starting point. That's your initial condition. We're going to be calling it P naught, P sub 0, that's your start. And what you're going to do is at that x naught, y naught point, so there, you're going to have an ordered pair there, x naught, y naught. You're going to calculate the slope there. The way you're going to calculate the slope is using your differential equation, dy dx, because dy dx is slope. So that slope's going to tell you where to go. You're going to ride along the tangent line with that slope for a distance of h along the x-axis. Once you've gone that h distance, you stop. Now you're at your new point P1. So you're going to calculate a new slope at your new point, because every point has a slightly different slope in the slope field, and you're going to ride along your new tangent line a distance of h, and then stop again. Then you'd be at P2. You're going to keep going until you get the value that you want. The AP exam never has you do more than 3. I'll probably have you do 4 maximum in class, and it gets a little bit tedious. Keep in mind they have computer programs that do this now with an h value of like 0.0001, and it can do it hundreds of times. This, we're doing it by hand, so h, the smallest h will be is usually 0.1. All right, so again, keep in mind we're getting approximate y values for a solution curve, but we don't actually get a formula for y because remember, we don't know how to find y usually. Here's a visual. I want you to draw this here. I'll only make you draw it one time. I just want you to have this to look back on. You're going to be starting at an x0 value. The distance here is h. In this case, h is clearly 0.1 because you're jumping 0.1 from x value to x value. So I start here. I calculate, notice I'm in a slope field. I calculate the slope at this point. I ride along that tangent line. Stop. Here is P1. This was P0. At P1, I calculate a new slope. It's going to be slightly steeper sometimes. This is the specific example, dy dx equals xy. We'll do it on the next page. So I'm going to get a new slope right along that slope. Stop. Then I'd find a new one. Notice here for this curve, which we'll be solving, is a concave up curve. So my approximation, which is right here, is a little bit below the actual x value. And again, that's because the curve is concave up. But it's an approximation for a reason. It's not exact. We're going to get to an example in just a second here, but I just want to remind you one more time. Up here, again, we are going to be plotting points, and we're going to be jumping from point to point using these straight lines, realizing that a straight line can approximate a curve due to local linearity, and whether we're concave up or concave down, that'll determine if we're above or below the curve, and realize we are just snaking our way through a slope field. All right, first example, here we go. This is exciting. I'm going to do an example out, and we're just going to do it intuitively, thinking about what we're doing without a table, and then I'll show you how a lot of people use a table to organize it. It's your choice if you want to use a table or not, but I want you just to think about what we're doing and have it make sense before you just go through the table way. So here's our first differential equation, dy dx equals x times y. I'm giving you an initial condition here, initial condition, and a step size of 0.1. There's our h. Now, the way you're going to do this is you're going to use the point slope formula of a line, which you learned many, many years ago and which we've been using this year. y2 minus y1 is mx2 minus x1. This is just a slope formula, and you move the x to the other side. So I'm going to isolate y2. So now I have this equation here. Now realize the change in x is like that h distance I was talking about. From here, oh my god, where's my pen? From here to here, our distance h, it's going to be delta x. It'll be constant the whole time because for every problem you have one h value and you run with it. So I'm going to replace x2 minus x1 with h. And then one other thing I'm going to do is notice whatever number you have here, the other side has the smaller number. So it's like to get a second y value, use your previous y value. To get the first y value, you use the previous initial y value. So we're going to start with this right here. Our y1, which goes with p1, starts with y0 plus mh. Now, when we do an example, this will make sense because this might look like gibberish right now to you. Some books write it with f instead of y. They like the function notation. I kind of like this way because it emphasizes that the slope is at the ordered pair, the previous ordered pair, but it's your choice, either one. So what we're going to do is we're going to start with P0, which is x0, y0, which is 1, 1. They told us that right here. That's our starting point. Now, the whole idea of Euler's method is you ride along a tangent line at this point for a distance of 0.1. So I need a tangent line here, tangent line at 1, 1. Well, I need a point and a slope. I have a point. Let's get a slope. To get a slope, that's dy dx. M is dy dx. So I'm going to get the slope at 1, 1. And here is my rule to get slope. You do x times y. So here's my x times my y. I get 1. So basically, I'm going to ride along a tangent line that has a slope of 1 for a distance of 0.1 units. And then I'm going to stop. My first job is to find out what will be the y value at that point where I stop. Now, I already know what the x value is, because if I start at p naught, which is 1, and I go a distance of if I go a distance of 0.1 along the x-axis, I would end up at 1.1. That is my x1. I need my y1. I have no idea what that is, but luckily I have this formula here, which says my second y value is my first y value plus mh. So let's take y1, which is right here. So 1 plus m is right there, the slope you just calculated. H is 0.1. That's the same for all of them. So I have 1 plus 0.1, 1.1. So this guy goes here now. Now that I have a second point that I've landed on, I had my initial point P1, I moved a distance of 0.1, now I'm landing at P1. So now I'm going to look for a new signpost. I'm looking for a new slope at this point P sub 1, because the slope is a little bit different there. Well, I'm going to plug in a dy dx again right here. This time I'm plugging in 1.1, 1.1, the next point. And the rule for dy dx says you do xy, always. So I'm multiplying, I get 1.21 for a slope this time. So now watch carefully. I'm going to do y2 equals y1 plus mh. This is called iteration, where you do the same thing over and over again, increasing the index as you go. So to get y1, you use y0. To get y2, you use y1. So now I want my second, or this would actually be my third ordered pair, the y value. So I'm going to use y1, which I have here. It's 1.1. I'm going to add to it the slope, 1.21, times the h value, 0.1. And when you do 1.1, you're going to have a calculator whenever you do these, but you get 1.221. I did this out ahead of time. So now what I have is I have p sub 2. That means P2 is going to have an x value of 1.2, because previously I was at 1.1. I go a distance of 0.1 again. That puts me at 1.2. I just found out that I would land at 1.221. So there is my third point, P2. So one more time, you have to remember where you actually want to end up. I want to get to 1.3 right here. So I have to do it one more time and then we're done. That means I need a tangent line to follow to get to 1.3. So I need a point and a slope. I have my point, I get a slope. The slope rule is x times y. Here's my slope. So to get y3, I'm going to do y2 plus mh. So the third y value will be the previous y value, which is 1.221, plus the slope I just found, 1.4652 times h, which is not changing. On your calculator, you would do that, and you'd get 1.36752. So that means my third point, which is x3, y3, is 1.3, 1.369752. So I can approximate to be this y value right here. You could write it like this. The reason you have squiggly marks here for the equal sign is it's not exact, it's an approximation. So since this was a separable differential equation, I want you to actually solve this by hand. So pause the video now. I want to see this work in your notebook. With your initial condition y of 1 equals 1, I want you to find that particular solution. Solve for y. You shouldn't have a c anymore. You have a value, constant. Once you have y equals, I want you to find y of 1.3 by plugging 1.3 in. That will be your actual value. Compare it to the approximation we got right here. Now, I want to show you this table because some people do a table, and your future teacher might actually do a table as well. So for this problem, you do a table with an n, an x sub n, and a y sub n. That's one way of doing it. Here, the way you set it up is n is the number of iterations. So you start off 0, and x sub 0, y sub 0 was 1, 1. That was our first ordered pair that we found. Our h step, jumping from 1 to the next iteration, is 0.1 for all of these. So I could immediately do 1.1, 1.2, 1.3. When we have x sub 1, y sub 1, it was 1.1, 1.1. When we did it again, we landed at a y value of 1.221. When we did it again, we landed at this y value, which is the y value we want. Your goal is always to find this column here. This is your iteration number, remember? And here is a visual of what we just did.